last video, we have discussed about this particular early stopping and also dropout regularization techniques. And what are these regularization techniques? Basically, regularization techniques are the techniques which are used to prevent overfitting. In order to prevent overfitting, in case of early stopping, what we are doing? Just we are reducing the number of epochs. Because of this, we are able to not overfit. And similarly, in case of dropout, what we are doing, we are reducing the complexity of the model by dropping out few random neurons in each epoch. Okay. So this is what we are doing in case of either early stopping or dropout. Now let's see the other two regularization techniques, that is L2 regularization, or we can also call it as ridge regression, and L1 regularization, which can also be called as lasso regression. Basically, in these, what we'll try to do is we'll try to change the loss function that we are using. So here we are trying to reduce the number of epochs, whereas here we are trying to reduce the model complexity. Whereas in case of L2 and L1 regularization, we'll try to change the loss function that we have so that it will not overfit. Okay, so this is the basic idea. Now let's discuss it in detail. In order to explain this, let me take one example, a regression example, where let's say X is our input feature and Y is the output that we have. Okay, and our data points, real-time data points, might look something like this. For these points, we might fit some hypothesis. And if you guys remember, there are three steps in any machine learning algorithm. First one is the hypothesis, and second one is our loss function, and finally we'll have our optimizer. So basically, what is the process that we follow? First, initially we'll initialize our hypothesis. Let's say our hypothesis is like this. Then it will have like loss, right? So these points are far from this particular blue line. So the loss will be initially high. As the loss is high, what we'll do with the use of optimizer, we'll try to reduce the loss. So like this, we'll reduce it and again find out the what is the loss, and again we'll try to reduce it. Like that, in a cycle, we'll make sure that loss goes very low. So this is what we'll try to do in general machine learning algorithm. But while trying to do this, what can happen is basically this is the training process, right? In training process, we are trying to reduce the loss. What will the model will try to do? The model will try to reduce this particular loss as small as possible. And if it is making it to zero, that means that our training loss is zero. If our training loss is zero, that is nothing but we are overfitting. So when will we say that our model is overfitting? When we have some hypothesis like this, right? So let's say my hypothesis is touching each and every point that I have. If my hypothesis is like this, then what will happen to the loss? Obviously, my loss will become zero on the training data, right? Why is that? Because it is touching each and every point, which means that the actual value and the predicted value for these points is equal. If both are equal, then loss will be zero. What is our loss function that we will be using in case of regression problems? If you guys remember, that is mean squared error, right? In mean squared error, what is our formula? Our simple formula is 1 by n summation of I from 1 to n, where n is the number of training data points that we have, y minus y cap whole square, where this is the actual value and this is the predicted value, right? In this case, both the actual value and the predicted value are equal every time. What will happen? This will go to zero. So that means that whenever loss goes to zero, that means that we are overfitting. This is what we can understand by observing this particular example, right? If we can somehow modify the loss in such a way that it will never go to zero, then there is no chance of overfitting, right? So this is what we'll try to do with the help of L2 and L1 regularization. So in case of L2 regularization, will modify this particular loss in this particular way. So this is our initial loss function that we have, y minus y cap whole square. To this, we'll be adding an extra term, that is lambda times theta naught square plus theta 1 square plus theta 2 square, so on theta n square. Previously, our loss function is only this one. Now we have an extra part, that is this one. Okay. So initially we are having a loss function only with this a. Now we are having an extra b term. So due to this extra b term, our loss will never go to zero. So let's try to understand this. And let me tell you what are these thetas. These thetas are nothing but our parameters. So let's say in case of linear regression or polynomial regression, what is our hypothesis? Our hypothesis will look something like this: y equal to theta naught plus theta 1 into x1 plus theta 2 into x2, so on, theta n into xn, right? So all these thetas will be my weights or parameters. So these we will be using over here. Okay. So lambda times we'll be adding all of this. Now what will happen? Now along model will try to reduce the loss, right? Previously our loss is only this part. Now model will try to reduce this whole part. Okay. So as it is trying to reduce this whole, what will happen if this is going to zero? Then obviously these will be having some value, right? These thetas will be having some value, some significant value. So this will be some large number. And similarly, when this is very high, obviously loss, if loss is only very high, then overall this sum will also be very high, right? So the model will try to balance out between this particular loss, that is this one, and also this one. So overall model will try to make this two very small value and also this two very small value, but not zero. Okay, it will not try to make them to zero, it will just adjust them to some smaller values so that our model will not overfit. So this is the basic idea of L2 regularization. So basically initially like this we might be having, and without this our model will slowly adjust our optimizer so that finally we'll end up being with a hypothesis like this, which is touching each and every point that we have. But as we added this extra term, whenever this is zero, this might be some large number. That's why it will try to balance out between this one and this one, and it will try to make the hypothesis somewhat better. Okay, so the better hypothesis might be something like this, means which is near to most of the points, but exactly not touching those points. Okay, so this hypothesis might be giving us some good result, better result. So this is about L2 regularization, and mainly L2 regularization can be used when you feel that all the features that we have are really important, like here x1, x2, so on, xn are our features, and if you feel all will be contributing to our output, then you can use this L2 regularization technique. But if you are not feeling that some of them might not be very useful for output, then you can go for the other regularization technique, that is L1 regularization, or we can also call it as lasso regression. In case of L1 also, the idea is the same. We are trying to change the loss function. So what is our loss function that we are having in case of regression problems? It is 1 by n summation of I from 1 to n y minus y predicted whole square. So the main problem is this is going to zero. So that's why in order to make it not equal to zero, we're adding an extra term. So in case of L2 regularization, what is our extra term? It is squares of the parameters, right? Now instead of adding squares, we'll be adding modulo values, that is theta naught plus theta 1 plus theta 2, so on, theta. This is the only change between L1 and L2 regularization. But the extra advantage that we have is it can enable us feature selection. Okay, how it can do that? Basically it can make some of these thetas to zeros. Okay, the model will be able to understand that this particular feature is not important, and it will make this corresponding data value to zero. And similarly, if model understands that xn is not important, then it will make that theta n to be zero. Basically it has to reduce this value, right? It has to reduce this and also this. So this obviously need to be adjusted to a less value. Along with that, while adjusting this to some smaller value, it will try to make the unimportant features parameters to zero. Okay, which will enable us feature selection. So this is the extra advantage that we have with the help of L1 regularization. But if you feel that all are important and those need to be used in order to produce our output, then we should be using this particular L2 regularization. So these are the two regularization techniques apart from this particular early stopping and dropout. where in case of early stopping, what we'll be doing, we'll try to reduce the number of epochs. We are not adjusting anything either in loss function, or we are not trying to change the architecture that we have. But in case of dropout, we are directly trying to reduce the model complexity by dropping out few neurons in each of the epoch that we have. Whereas in case of L2 and L1 regularization, we are directly adjusting the loss function so that it will never go to zero. Basically, the loss that I'm talking about is the training loss. Okay. So I hope this video is very clear for everyone. And if you have any doubts, please comment down in the comment section. Thank you everyone, and bye bye.